pretty much everyone who has done something very, very important in C++ is here at least every other year or so. Directly interfacing with those people is just an incredible boon to your career, especially early in your career. Getting to pick people's brains on things, just hanging out, talking with people, you can't put a price on that. And you don't get those online.
Okay, welcome. Thank you for staying till Friday to hear this session. My name is Michael Wong, and along with my colleagues, Maggot Michael, Paul McKenney is not here, we want to talk to you about a few of the interesting upcoming features from low latency, parallelism, and concurrency. That's been an area that we've been working on all our career. So we like to generally we like to identify these features since the last CppCon. So basically, since then, we've had 3 meetings of the C++ standard. There was one in Kona in 2023. There's one in Tokyo. There was one in Tokyo in March, and then one in St. Louis in June. Yes, we sometimes go to some interesting places. Okay, so what we do want to talk about is we want to talk about improving C++20 atomic min-max, which is in paper P0493. You can find these papers by typing wg21.link/P0493. That will always get you the latest version. We're going to talk about hazard pointer extensions in P3135. We're going to talk about pointer tagging, P3125. And I'm going to continue and give you an overview of how where parallelism has been and is going, and by guiding you through parallel range algorithm. And if we have time, we will talk a little more about parallel algorithm. Most likely we won't. There's a lot of material here. This talk is trying to be extra technical by diving into code a lot more than concepts, motivations, okay? So you guys know me. My name is Michael Wong. I'm a DE at CodePlate/Intel. And let's start with C++26 atomic min-max. So as of C++20, atomic operations like fetch, add, and compare exchange are supported, but fetch min and fetch max are not yet part of the standard library. Even in C++23, which introduced new features like coroutines, ranges, and other areas for standard libraries, but atomic minimum maximum, believe it or not, is still not in there. So there was a paper that talks about this. Oh, I'm going the wrong way, sorry. All right, so atomic min-max dates back pretty far, back to about 1980s, research on parallel computing. And many platforms like OpenCL and CUDA already support atomic min-max, so it is needed in C++. So especially in multi-threaded environments, race conditions can arise when multiple threads attempt to update a shared variable simultaneously. And this can lead to data corruption and unpredictable program behaviors. So atomic min-max operations address this issue by ensuring that updates to the shared variables, basically perform atomically, meaning that they are indivisible and cannot be interrupted by other threads. So atomic min-max operations offer a lot of benefits. They give you an efficient and safe way to concurrently update shared variables. They eliminate the atomic min-max operations. They eliminate the need for explicit locking. And this can lead to basically improvements in performance and scalability, especially in highly concurrent scenarios. Now, additionally, atomic min-max gives you the ability to implement lock-free data structures, which further enhance performance. So this is the proposed interface. Okay, the color's not too bad. Hopefully you can see that. I was trying to highlight all the keywords and all the variables so that you can distinguish them. The C++ standard library gives you the ability to do atomic min-max operation using the stud : atomic template class and its member functions, fetch max and fetch min. Now these functions atomically update the shared variable with the maximum or minimum of its current value, and then And in a way, this is similar to other atomic operations like fetch add, which already exists. If you look at some performance data, you'll see that the hardware support can be significant, okay? It can be significantly faster. This is basically a graph that shows benchmark results comparing the time and contentions across multiple cores. So what this does is that it shows that the hardware instructions outperform a cast loop, a compare and swap loop, as the core count increases. But it also shows that the performance scales well with the core count. So right now, you can actually, the standard gives you the ability to implement it if your hardware supports it, okay? Here's the code example. Now, this is an excellent example to demonstrate the usage of atomic fetch max operation in a multi-threaded environment. So in this example, we basically have multiple threads concurrently searching for the maximum value within a different range. And each thread uses atomic fetch max to atomically update and update the shared max underscore value variable. The final value of the max value represents the maximum value found. So it's a pretty basic idea. Let's walk through the examples. So first of all, like I said, this program finds the maximum value in the range from 0 to 999 using parallel processing. It demonstrates how atomic fetch max can be used for thread safe updates in a reduction operation, basically. So the key component here you'll see is that there's a std : atomic angle bracket int max underscore value. And that's basically a shared atomic variable to store the maximum value. There's also a find underscore max in range function. And this processes a subrange and updates the max value. There's the main function, which creates and manipulates and manages the threads, each processing a subrange. So let's look closely at the find max in range function. This basically takes a start and end value, defining a subrange. It iterates through the subrange, updating the max underscore value using fetch underscore max. It uses memory order relaxed for efficiency, meaning that the order doesn't matter. Usually in things like this, when you're looking for the value, the max, the order doesn't matter, just like in a counter. Next, let's look at the thread creation on the right side. This creates 10 threads, each processing a range of 100 numbers. So thread 0 processes 0 to 999. Thread 1 processes 100 to 199. Thread 9, obviously, processes 900 to 999. Let's look at the atomic operation. So the atomic operation is max underscore value dot fetch underscore max, parenthesis, I, comma, std : memory order relaxed. So it atomically updates max underscore value if I is greater. And it ensures thread safe updates without explicit locking. This is lock-free programming right here. It's reachable now to everyone. That's the significant thing. You don't have to be an expert now. Well, you still have to be a little bit. Question over here, yes.
Why only one memory layer and not two?
That's because the fetch max takes care of it, inside of it,
But
yes.
I may want to have two different ones depending on whether or not it was updated.
And you can do different ones later, yeah. So continuing on, the thread joining on the far right side at the bottom, this is necessary because the main thread waits for all the worker threads to complete, and then it ensures all the ranges have been processed before printing the result. The result is going to be the final max underscore value, which is going to be obviously 999. Nothing tricky there. This is the largest number in the overall range. The benefits of this approach is parallelism. It utilizes multiple cores, okay, for faster processing on your CPU here. We're going to show you how to do it in your GPU later on. It gives you lock-free programming. There are no explicit locks, and this reduces contention and overhead. The less locks you have, the less contention there will be. It's simple. It's atomic fetch underscore max simplifies the implementation. Now, I talked about memory ordering, and I've been deeply involved with atomics and memory ordering for about 20 years now. 25 maybe. So I just want to ask, before I go through this, does anybody here wants me to go over what memory ordering means? What do you think? A few. Looks like you guys all know memory ordering pretty well. So I will just lightly go over it. They're really basically 4 kinds of ordering, as you can see. Sequentially consistent is the strongest. Acquire and release is the next weakest. And then after that, you have acquire, release, acquire or release. And then, of course, relax. Okay? Basically, all I'm going to say is that memory order relax gives you no synchronization or ordering constraints. It gives you only atomicity and no ordering constraints. It's the fastest, but it's also the least guaranteed. You use it when order doesn't matter, like incrementing a counter, finding max. Memory order acquire, however, ensures subsequent reads sees the effects of this operation. So all memory operations after the acquire operations are not reordered before it. And this is like putting up a read barrier. You want to see all the changes made before the lock was released. This is used when you are loading a shared state, like reading a shared flag before accessing the shared data. Order release makes prior writes visible to subsequent acquire operations. So all memory operations before the release operations are not reordered after it. It's like putting up a write barrier. You want all your changes to be visible. Example use cases are like storing shared variables, like setting up a shared flag after modifying shared data. And then there's this combined one called acquire release together. And this obviously combines acquire and release. And it's basically both a read and write barrier. It's useful for operations that both read and write a shared state. So it's useful for basically read, modify, write operations or atomic exchange operations. And then the final one, the sequentially consistent, is the strongest. Global consistency, total order across all threads. It's the slowest, but it's the most understandable. Okay? And it's the default if you don't say anything. So you should say something unless you know. And when you need to, this is basically what you use when you need to ensure specific order of operation across all threads. So I'm going to stop there. So basically, in conclusion, atomic min-max operations empower C++ developers to tackle the challenges of concurrent programming with confidence. They provide a powerful mechanism for managing shared variables and give you the ability to create lock-free data structures. Okay? Now, there is a follow-on, which I'm not going to explain a lot, but I want to tease you that there is atomic floating point min-max. And atomic floating point min-max are fundamental building blocks for many concurrent algorithms. While we added atomic integer min-max, the floating point versions were removed from the proposals in C++20 because there were some concerns about the behavior. This includes the fact that the semantics of floating point min-max basically have evolved in C++ to address the challenges posed by the corner cases. And what are these corner cases? Well, the standard library functions std_min and std_max exhibit undefined behavior when you're dealing with nans. And this basically makes them unsuitable for robust floating point computation. Currently, the std_min_max have some other unintuitive behaviors, like they treat -0 and +0 as the same. They're equivalent. And this is not 754 compliant. So what we did in this proposal is that we follow what the C functions have. They've actually evolved a little bit further than us. So the C function have fmin and fmax. They give you more predictable behavior by basically treating nans as missing data. That's the right way to treat nans. The other thing is that their handling of sign zeros can be implementation dependent. So the newer C++ functions like fminimum, fmaximum, fminimum _ num, fmaximum _ num, gives you explicit control over nans and consistently treat -0 as less than +0, aligning with IEEE 754. And there's also now growing hardware support for these operations. GPUs, for instance, as you know, I worked a lot in GPUs, have had them for a while, and we're seeing them appear in more CPU architectures. There is more to this, but I want to use this chance to hand over to my colleague, Megan Michael. And first of all, ask him to introduce himself and come up and take over. Thank you.
Thank you, Wong. So I'll cover two papers that were presented to SG1 and received unanimous support for continuing. So the first one will be about extensions of hazard pointers beyond what's in C+26. So I'll just give you hazard pointers were voted by plenary. Thank you. Okay, so yeah, hi everyone. I will talk about two papers that were presented to SG1 and received unanimous support. Is it okay? So yeah, as I mentioned, I'll talk about two papers presented to SG1, and they received unanimous support to continue. They may be targeted, like, unlikely to 26, they'll go beyond to 29. The first one is hazard point extensions beyond C+26. And for background, I'll talk a little bit about what it is in hazard pointers in 26. It was voted last year by plenary to be included in the standard. So the very general idea is that hazard pointers, they protect dynamic objects that could be removed concurrently, and they prevent them from being reclaimed while being used without any further synchronization. And you can see here, like on the left side, that's like the user of hazard pointer, the one who wants to protect objects, and it's extremely low overhead protection without like locking or atomic instructions and things like that. On the right side, that could be a concurrent, like threads that are removing the object. They can't delete it right away. They have to retire it, which basically they're giving it to the library, say, you can remove it, you can reclaim it whenever it is safe to do so, when it's unprotected. So that's kind of like the general. So like the reclamation is, at least in 26, is going to be asynchronous. And usually it is amortized, so it's kind of like a whole bunch of reclamations happening together to make like the cost per object constant, amortized. All right. So this is a quick view of this is the whole API. This is for 26 for hazard pointers, and I'll just focus on the main points. Is that there is a class template for objects that are protectable by hazard pointers. These are like the objects that may be protected by threads that want to access them or read from them. So the only member function there is retire, and this is used by the remover. So whoever removes the object and it's no longer reachable, they are responsible for retiring it instead of deleting it and handing it over to the library. The hazard pointer object itself, there's just like things to note is that the default constructor is an empty hazard pointer, and it's very cheap, like basically not like nothing. The main function that an empty hazard point cannot protect. So there's a free function, make hazard pointer. This is the one that constructs a hazard pointer that can be used for protection. And this takes like typically a couple of nanoseconds or so. And then the protection functions, these are like protect or try protect. One is unconditional, where it kind of like it will get, you give it an atomic source, and it will get a pointer value that is protected. Whereas try protect, like you give it a pointer value and say, can we protect this from that source, and it may succeed or fail. So actually protect is basically a loop of try protect. So anyway, that's just a very quick overview. A very simple example here is that, again, using the C++26 API. So here you have an object type T that is protectable by hazard point because it inherits from the class template, and then you have the read and access, and this is supposed to be fast and frequently called. So here it uses a hazard pointer. It uses one that is non-empty to be used for protection. It uses to protect a pointer value from the atomic source. And then once it's protected, it can use it as it like. There's no limitation on the duration of the user function. There is no limitation on what locks it can acquire using other hazard pointers. Retiring doing an update and retiring an object, all this stuff, there's no restriction. So these are kind of advantages of the technique. All right, so far this background. So now I'm gonna go to the paper that was presented to SU1 in Tokyo in March. So these are extensions beyond 26 to make it more robust, more faster. And in that paper, we actually analyzed several ideas, and some ideas we actually told the committee or told SU1 that actually we don't think that these should be considered for now, because we can already do enough with 26, but yeah, so it's like there are higher priorities. And so there's counting, which is a big topic. And it's like these are these are not obvious things. They are in the paper, and it's actually probably would be a good topic for a future talk. So I'm not going to cover that in this presentation. The other topic where do we do asynchronous reclamation? And I get that question a lot. Like, do you require to have a dedicated thread pool for that, or do I have an extra thread, or I don't want to have an extra thread? So I'll talk about that briefly. We're not doing extension with that. The other things that we are proposing to the committee, and we received a unanimous support from SU1 to continue, but then they gave us feedback on the API so that will be future cycles of future iterations with the committee until we get the right API and wording and so on. So these are synchronous reclamation. That's a big topic. And batch creation and destruction, it's like relatively smaller, but just like an optimization. So I'm going to talk about these three topics that I marked. The first one is we're not extending this execution of asynchronous reclamation. And I just want to point out that, so I mentioned retire. Retire is basically you have an object that you removed, and you're giving it to the library and say, reclaim it whenever it's unprotected. It's asynchronous. We don't care when it is done. It's just going to be done by the end of the program. And usually a well-implemented library would guarantee a bound on the number of objects that are retired and reclaimable, but not yet reclaimed. So there's it's not going to run out of memory. So anyway, so in the first snippet, we're calling retire inline. So as I explained, this might trigger asynchronous reclamation. And asynchronous reclamation is amortized. It's a whole batch of reclamations that might be unrelated to this thread even. And it might be like tens of thousands of objects. So in some cases, we don't want the worker thread to be stuck with that. So that's where using the C++26 API, we can do the second snippet where we can just submit a task to an executor to do the retire. So that's a little bit extra overhead than a retire that is aware of where to, that's kind of preset to do as an executor, a dedicated pool for reclamation or not, but it's available. We can do that. We will be able to do that with 26. So we're not doing anything about it, at least for now. Okay. All right. The other topic there for extension, this one is we are proposing it for probably for 29, is synchronous reclamation. So I mentioned asynchronous reclamation. We don't care when it is reclaimed. Here's an example where we would care. So look at this, a shared container on the left and the right. So I'm going to go through the left one a little bit here. So we have a shared container. It uses objects, let's say nodes in in a in a linked structure. And these objects are protectable by hazard pointer. They inherit from the class template. You can do insert and erase, and then when you do erase, we call retire. We just like give it to the library. We don't care when it is reclaimed, right? Now there's a class A. This one, its deleter does not depend on any independent resources that have independent lifetime, right? In that case, let's go. We instantiated a container with type A, and we did insert and erase, and now there's an object A that may or it got retired, right? We know that, and then the container got destroyed, right? The end of the curly brace. Okay, so now we reach the point where an object containing A may be not deleted yet because it's asynchronous reclamation. But then that's okay because the deleter of A does not depend on resources with independent lifetime. So that's like, but then that's restrictive. That's telling the container you can only handle the types like similar to class A that don't have dependence in their deleters. Okay, now we want to make it more general purpose, and that will go beyond C++26. This one, the example on the right side is wrong, like by using C++26. In that case, let's look at the same thing, but then it's a class B that has its deleter is dependent on a resource with independent lifetime. So now we went and instantiated the container, but with B as a template argument. We insert an object B and erase B, and then now we destroy the container. But then the object might still be around because we only have asynchronous reclamation. So, and now we destroy the resource. When like asynchronously, the destructor of that object or reclamation happens, it's gonna blow up because it depends on a resource that's already gone. So for C++26, we're not allowed to, library writers are not allowed to do this general purpose. They'll say, okay, you have a container, but you can only use it with this kind of more restricted way. I mean, it covers a lot of things. I mean, you can have, class A can have like vectors and shared pointers and hash maps and all this. So it's quite powerful, but not as powerful as we want it to be a really general purpose. That on the right side. Okay, so that's the motivation there. The proposal here is like some technique called cohorts, and I developed that in between like 2018 and 2020. It's fully implemented in Folly, the open source library for Facebook, has been in production for that many years. I mean, 6 years or heavy use in production. I talked about this whole experience in a lot of detail about the implementation in CppCon 2021. So there's a full talk about that if you're interested in the implementation. But then we went to the committee with a proposal to include it in the standard. And of course, we got like unanimous support, but then also there was feedback about the API. So if you look at the paper I mentioned, like 31, 35, it's going to be different API. So this is what we're going to go back to the committee in the next standard meeting in November. So in this proposal, its cohort is just like, it has a constructor, destructor. The semantics of the destructor, it is that it's a cohort that will include like objects, protectable objects, anything that got retired to it. And then the destructor of the cohort will guarantee that all these objects have been destroyed. So that's like, these are the semantics. Otherwise, it's like not movable, not copyable, and that's like the interface for the cohort. For the protectable objects, we will add an extra function that is called retire to cohort. And the semantics are slightly different from retire, the regular retire that I mentioned for C++26. In this case, retire was kind of asynchronous, like saying, well, you can retire it now, retire it later, put it in a, submit to an executor, that's fine. The reclamation can happen any time later when it's safe, that's fine. Here, we're retiring to cohort, that's synchronous. We have, it has to happen now when you call this function. So you cannot just give this retire to cohort to a separate executor. Do it now, but then we're separating the part where a retirement can trigger the big reclamation, the asynchronous reclamation. So you might ask, why are we participating in asynchronous reclamation? Because the cohort might be very long-lived. We might have billions and billions of objects, and we don't want to run out of memory. We want to participate in asynchronous reclamation. So we propose a free function, asynchronous reclamation, which is kind of we're okay with this to be to do asynchronous reclamation that may take very long time, do tens of thousands of objects that are unrelated. That's totally fine. So that's these are the semantics that we want. Okay, so now let's go to an example, and we're revisiting the container examples that I mentioned earlier. So it was broken if we don't have synchronous reclamation, but now with the cohorts, we're gonna give it that ability to handle any type of object, any type template parameter that whether it's dependent or independent of resources that have independent lifetime. So anyway, so now let's see what changes we made here. Now we added a cohort, an instance of a cohort to the container. So why is that? Because once we destroy the container, automatically we're going to destroy the cohort. What does this mean? That the structure of the cohort will guarantee that any object that we retire to the cohort will be completely reclaimed at that point. So that's kind of that's how it works. And now we change erase. We made two small changes there. Instead of just a regular retire, which has two things to it. One is retire give it to the library to take care of reclamation, and another is potentially trigger asynchronous reclamation if let's say we accumulated so many retired objects that may be reclaimable. So here we change it to say, okay, synchronously, we want to say retire this object right now to the cohort, because once we destroy the container, we want this object to be destroyed synchronously. But then also, in this case, we're submitting it to a dedicated, let's say, thread pool for asynchronous reclamation. We're saying, well, try to do asynchronous reclamation. We don't care when, because if the reclamation happens after the destruction of the cohort, that's fine. I mean, we don't, we're not participating in that specifically. But if this is a really long-lived container, we want to do asynchronous reclamation. Okay? So then you go down, okay, class B, that's the same. We didn't change it. We didn't make any requirement. That would be it uses the independent resource. We go there and we have the resource. We instantiate the shared container. We do the insertion, erase, and close the curly, the brace, right? Here it's so if you remember on the left side, we said it's okay because there may be objects of type A that are okay. All right. So in that case, it's okay. But then there will be reclamations happening, but it's okay. But on the right side, it's okay because the objects have been destroyed by the closing of that curly brace when the container is destroyed. All right. So anyway, that's the proposal, and as I mentioned, this is the example. Okay, moving on to another proposal. This will be a simple one. It's like batch creation and destruction. And here's just like for, as I mentioned, creating a non-empty hazard pointer, it does have a little bit cost, like accessing thread local and things like that. And instead, like let's say we have a snippet here that uses 3 hazard pointers, non-empty hazard pointers. It will do that, like, let's say it takes 2 nanoseconds, for example, it will take 6 nanoseconds. The proposal here is like just we provide a couple of free functions that do, will allow the library to batch create and batch destroy. So in that case, we could just do the whole thing in a couple of nanoseconds. So that's kind of, it's a simple optimization, and the interface here is like we're going to provide it with like let's say an array of of empty hazard pointers, and then these functions will make it non-empty or they'll empty them. So that's that's it. I mean, so hopefully will be like simple. Like the comments from the committee would be straightforward there. Okay, moving on from this to another paper. Pointer tagging is, the proposal here is that if like let's say they're aligned, pointers to aligned types, they have like bits that are guaranteed to be 0, either like at the low bits and the high bits. So this proposal is like motivated by, as like, I quote verbatim from the paper here, is that this has been happening for decades in practice, but then the standards say that this is undefined behavior. So let's standardize it and make it safer for programmers to do this. So the feedback was very positive from the committee, except that they said, like, let's not do the high bits because we don't know if vendors are, will make use of that. But it's good to do the low bits. So like going forward, it's only the low bits probably. Okay, so here's the API. The main thing is a class template tagged pointer. That's like a pointer that may be tagged in the low bits. And then there are 4 function templates that provide one of them. The first one is like it provides a mask of what are the available bits for tagging, like given the alignment. The other one is the other functions are to convert from a pointer to a tag pointer by giving a tag. So you take a pointer and a tag, and you convert it to a tag pointer. The precondition that the tag would be fitting in this mask that we mentioned in the first function. Then a conversion from tag pointer to extract the pointer from the tag pointer, extract the tag from the tag pointer. So that's kind of the proposed API. Here's an example using these functions. I'm not going to go through it in too much detail, but it's just like this is so actually, I should say this is not in the paper. I made up this example because I wanted to do atomics, and there was no atomic example in the paper. So any errors are mine, not the paper's author. So here you can see we can make an atomic for a tag pointer, and then do atomic load, atomic compare exchange. But then use extract the tag value, check the tag mask, tag the pointer. So this like using the interface. Okay, all right. One last slide before I hand it over to Michael to continue. Here's like saying, okay, if we get this, so I'm very excited about this. If we get tag pointers in the standard, I would follow up with hazard pointer to support tag pointers. And as I mentioned, there are lots of like good algorithms, like low latency, high scalability that depend on these pointer tags. So now it would be available to use. So here I mentioned the protect and try protect functions in C++26. Possible extension would just apply them instead of atomic source on T star. Apply to an atomic on a tag pointer, and use it that like as simple as using the interface that will be in C++26. All right. Thank you, and Michael.
Thank you, Maggot. That was great. All right, so I'm going to move to talking about bringing parallelism to stood ranges algorithm. So let's step back for a moment, okay? So I've been involved with ISO C++ parallelism pretty much since the beginning in 2004. And at the beginning, there was C++ concurrency plus, where we're trying to build the memory model, make it so that it's not just solely sequentially consistent, so that it has weak acquire and release. We really cared about that because at that time I worked for IBM and PowerPC were very weak architectures. So Paul McKenney, Maggot Michael, and I was deeply involved with trying to work with that, building up the weak memory model, the forward progress. So in C++20, we had things like concepts, ranges, modules being added, and then concurrency had more people wanting to come in, and they talk about things like atomic ref and barriers, semaphores, okay? The big thing going back is that in C++17, the big improvement was parallel algorithm, okay? That's right the first again, and many people contributed to that. So moving on to C++23, there was ranges, and there were many people that got involved with that. There was multi-dimensional spans, as well as operator now potentially square bracket. This effectively gives you the ability to look at C++ arrays like an array that most people are used to, especially if you've been in high-performance computing or mathematics for a long, long time. Otherwise, you have to do this weird template stuff with parentheses, and some people get confused. This is a function call, is this an array? Okay, all right. So we're now in C++24, but looking ahead for 26, this is what I see as what's coming, okay? So you've got executor, sender, receiver. That's going to give you a uniform way of dispatching functions, not just to CPUs, but pretty much to any accelerated devices. There's going to be reflection. That's like a big theme that's been talked about here. There's going to be algorithm, and that's going to be talked about things like asynchronies and ranges. There's going to be linear algebra, okay? And that's going to involve sub-MD span and padded layouts, controlling exactly where the bits are being laid out. That's pretty important. And then more concurrency plus. So we have Maggot and Paul and I have put into C++26 draft already. So it's already been voted in. RCU, read, copy, update, another lock-free algorithm, hazard pointers you just heard. Okay, and of course SIMD is coming. So all in all, I feel that this is a good place to be in the future of where parallelism, concurrency. Our goal has always been to give you the low-level building blocks and then incrementally give you more and more higher-level abstractions. And this talk actually highlights some of those abstractions really well, okay? So I'm going to talk specifically about the evolution in that in C++03, there was this basic serial sort using iterators, right? You see that code up there? I don't think I have to go over it. I think almost everybody in this room is pretty high up in terms of knowing this stuff. So that's why you're here, I think. So C++17 introduced execution policies to support parallel and unsequenced execution. That's the stuff that in that brownish, reddish, whatever that thing is, that says execution policy, ref, exec, okay? The rest is pretty standard, there's like an iterator, another iterator, and then there's like a compare for what you're looking for. Then C++20 came along and it introduced ranges, range-based sort. So that got rid of the iterators, right? And this really improved expressiveness and safety. So for next C++26, what we are proposing, I'm also working at Intel, actually. So this is actually one of the Intel proposals. It's P3179. And what it's doing is it's going to combine what's in C++17, the execution policy, and in what's in C++20, the range-based sorting, and offer basically the best of both worlds. That's the next step. We try to be very deliberate and very careful as what we do. So the evolution. from iterators to ranges, 1. Number 2, the addition of parallel execution support. Number 3, the introduction of projection functions in ranges. Number 4, using concepts like random access range and sortable. 5, cons expert support. 6, it's more expressive return types. I didn't work on all this, but it comes together nicely, and it just always happens in C++. In my career, that's just, I don't know, I can't explain it, but that's just the magic of it. Okay, so C++ 17 gives us parallel algorithms. So it's just exactly what I said before. We want to combine the power of ranges and parallelism. And we need this because the users often combine the range and parallelism, but the current approach is verbose and error-prone. And this proposal is going to offer a more natural and expressive way to parallelize range-based computations. Okay, so what are the key modifications we made? So this proposal basically is to add, so there's what's called execution policy that came from the parallel algorithms. There is the random access iterator, random access ranges. Even I'm still falling into that trap. I'm old, so I still remember those days. Algorithms that require random access ranges for efficient parallelization. There's going to be bounded ranges, so at least one input and the output range must be bounded, okay, for safety and performance. And then the algorithm return type that's consistent with the serial range algorithms for easy migration. So what this does is it's going to enable single cell, single call fusion of multiple operations. Okay, so let's take a look at some code. So the return type, so we've made these design decisions. Notably, we're requiring the random access range for now to ensure efficient parallel execution. And we're taking ranges as output to improve the safety and to simplify the use cases. So here's an example of how the API look for each of these. Okay. So the code defines a template function for a parallel version of std range for each. So let's break it down. Okay, let's start with the template parameters of this one. Okay, so the template function for indirectly unary invocable takes a projection function. So in there's an execution policy that specifies how the algorithm should be executed. So that's sequential parallel. That's from C++ 17. There's R, the range type that is constrained to be a random access range. There is projection, a projection function that is defaulting right now just to identity. Okay. There's fun, the function that's going to be applied to each element constrained to be invocable with the projected range elements. Next, let's look at the requires clause that brings in C++ concepts. So this require of a size sentinel for bunch of angle brackets. And what it says is that this ensures that the range R has a size sentinel, meaning the distance between the beginning and end can be computed in constant time. The return type, okay? So it says the return type is a range colon borrowed iterator underscore T of angle bracket R. So this returns an iterator into the range. The borrow iterator underscore T basically ensures that the return iterator is safe to use even if the range was passed as a temporary. The function signature, that for each execution policy, all ref, fun, projection to defaulted to identity, takes an execution policy, a range, a function to apply, and an optional projection. And the ref for policy and R allow for perfect forwarding. So the key points that you notice here is that this is a range-based version of for each, meaning it operates on a range rather than a pair of iterators. Pretty simple transfer. It's designed for parallel execution, as indicated by the execution policy. You could, of course, turn it off and just enter seek for sequential. The random access range requirement ensures efficient parallel execution processing. The size sentinel 4 requirement allows for easy partitioning of the range for parallel execution. And then the use of concepts like random access range, indirectly unary invocable, gives a clear compile time error if the range are not met. Everything just comes together. The projection parameter allows for transforming the range elements before they're processed, before they're passed to the function f. Okay, so the function template gives you flexible, type safe, potentially parallel way. Thank you, somebody nodded, so you knew you know that was coming. To apply a function to each element of a range with the added power of optional projection. It's modern C++. It's our modern C++ approach to algorithm design, to leveraging ranges, concepts, and parallel execution. Okay, I got 10 minutes left. So what's the difference to C++ 17 algorithm, parallel algorithm? But by now, you probably should know. It's that parallel range algorithms require random access ranges, and the output can now be a range instead of just an iterator. What's the benefits? The benefits of this approach are significant. We get more expressive code, potential performance improvements from Fusion, safer APIs, and an easier path to parallelism. This is the high-level stuff now. No longer are we building all the lower building blocks. Okay? Now, I won't have time to go over this because I want to leave about 5 minutes for question, but I want to tease you with the next big thing that we were working on, parallel algorithms. It's a natural fallout. So today, there's the idea of parallel algorithm. It's in P2500, which is a follow-on to P2300, which is where the sender-receiver executive stuff is, which was just voted in, by the way, in St. Louis, the meeting about 3 months ago. It did clear the vote, kind of just barely, but now it's going to have to go to national ballot and see whether the nations accept it. Okay, it was tight, but we knew that was going to happen. Okay, same slide about the evolution. Don't need to go through it. But look closely at C++ 11.14, where you basically have, well, this basically is just a std vector named vec with n elements. That's 0 initialized, and the size n is presumably defined elsewhere. Then we also get what I talked about last, P3179, the parallel range improvements. And what this does is that you have std range generate, so this basically generates random values in vec using the std : min std ran random number generator. And then the second function in that group, coming out of P3179 that I talked about, is the std range sort, where I'm going to sort the vector vec using the parallel execution policy, std execution par, which correspond to parallel. This sorting is done in parallel across multiple threads. I could also do it, in a SIMD manner. Okay. So what's important? So this line utilizes C++20 range library extended by P3179 to allow the use of execution policies with range-based algorithms. The generate algorithm populates the vector, right? And then the sort then sorts the vector, all in parallel. Wonderful. Now we're going to add schedulers. So here what we have in P2500 is that we want to support the ability to do schedulers to specify where to execute. Now, P2300, the executor sender receiver, has a basic scheduler, but it's not going to be great for a lot of things. We are encouraged to create our own scheduler, and what this is it allows you to say where it's going to be executed, in addition to how it's going to be executed, parallel, sequential, or in SIMD. Okay, so we have a function, std execution, execute _on, that takes some scheduler, and in this case, a sequential policy. So this basically combines a scheduler with the sequential execution policy, and the scheduler determines where the code runs. That could be on a specific CPU or on a GPU. While the execution policy controls how the algorithm executes. in this case sequentially. Should range generate and should range sort. Like before, these algorithms generate and sort the vector the vector. Sort is done in parallel in this case. Okay? I selected that. However, now they're influenced by the scheduler, which may execute these operations on a specific hardware resource as dictated by some underscore sched. The relevance of this is that the P2500 proposal introduced the concept of schedulers to C++ algorithms and allow developers to specify not just how, the execution policy, but also where the computation should be performed on a GPU or a CPU. That's fine-grained control, as well as over the execution context, as well as high-level abstraction. Crazy, right? I'm not going to go through this because I have way more slides than I could. But I will talk, I think I also want to bring the group maggot up with 5 minutes left to field some questions. Okay, but I will close by saying that we've basically covered a few interesting proposals that are coming in C++ parallelism and concurrency based on the last 3 C++ standard meetings since the last CppCon. We do this pretty much every year. So we covered improving C++ atomic min-max, as well as, and I hinted at floating point, which is almost as far, which is also going to be included likely in 26. Magus talked about hazard pointer extensions with cohorts, synchronous reclamation compared to previously asynchronous reclamation, pointer tagging, using the pointer tagging ability to augment hazard pointers. And I talk about parallel range algorithm and a little bit about parallel algorithms. 1 and 4 are very, very likely to make C++ 26. 2 and 3 probably will be beyond. You should ask Maggot. So these are just some of the likely features that have, that fit in a talk format and is of interest. Okay, so I want to bring Maggot up, please. Okay, yeah, and I'm going to turn this up. And that way I can use that guy or this guy, right? Yeah. All right. So you can
Let's use this if needed.
Yeah. Questions, please. Got 3 minutes left.
Hello. I had a comment about the pointer tagging.
Yeah.
I find it kind of unfortunate that it allows only for the low order bits, and I understand why that decision was made. Because you can't really know like how many high order bits are available depending on the addressing scheme or whatever, right? But I wonder if you could somehow say provide control over that by saying like allowing the user to specify how many high order bits they have available. That's what we do on our system. So for instance, we know that we on some of our platforms we have 16 bits available in a high order, and we make that choice. It's up to us to specify how many high order bits are available, right? I just wonder if that was considered during the proposal, or is possibly, yeah.
I can barely remember it, so.
Oh, sorry.
Maybe,
No, because
yeah.
You were talking about the high bits.
Yeah.
Yeah.
Yeah. So the response from SG1, I mean the author who proposed this was proposing like let's look at all of it, but then SG1 said they expect this to be a problem with some vendors, and we don't want to tie their hands in the future to use these bits.
Well, what I mean is, you could say as one of the template parameters that the high order bits is by definition by default, set to 0, and but allow allow the programmer to override that. So like on my platform, I know that I have 16 bits available in the high end, right? And so when I create my tag pointer, I should be able to have get those bits available to me.
I think
without that kind of feature, it's kind of not so useful in my particular context.
Yeah, so I think even today, like people like you and many others, like we do use these high bits, but it's not sanctioned by the standard.
Well, the standard is evolving.
Yeah.
There's still plenty of time
Right.
to add a feature like that.
Yeah.
Yeah.
If you write us a note, we are going to be able to try
sure.
to convince the author in the next meeting. Yeah.
That's just why I'm just making that comment now. So.
Yeah, no,
Okay,
I think
no,
it's an excellent use case. The question is so we can debate this and represent
Sure.
your thoughts. Thanks, David. Yeah.
Thanks.
Hi, thanks for the great talk. I have
Thank
one question regarding like parallelized algorithms. I'm wondering because I have a use case where like I want to do parallel calculation over a cluster of loads. Basically, I want to send the data to other loads and send the function to other loads and do the calculation. Currently, when I implemented the issue, kind of it's mostly about like serializing the function because function is not serializable like in some sense. So I need to cannot use lambda for it because I cannot serialize lambda. So I have to work all the functor with some customized data structure. I'm wondering is there any proposal by any author to add support to run parallel algorithm over a cluster of loads, by sending data to other loads, by sending the function to other loads.
Okay, so I think what I heard was that you want to be able to selectively serialize some part of your range.
I think we segment the range to multiple parts and then send one segment to each node.
Oh, so you want to serialize it, but send different parts of it to different nodes.
Yeah.
Yes. Okay, so I think that that's where different schedulers will come in. Okay, that's where you're going to talk about where you're going to send them. So you're going to have to craft your scheduler carefully enough so that it can be distributed to different nodes because it's more local, right? The data is more local and it's attached. It's closer to that node. Okay. I think we should talk after and see what we can do about that. Okay. All right.
Cool. Thanks.
Thank you.
Just a quick question about schedulers again.
About what?
The schedulers.
The scheduler. Yes.
Would it be the place where we can set thread affinity to some specific
Can you
cores?
louder? You want to set what?
The thread affinity to
Oh, the
some
thread affinity.
specific
Yes.
cores.
No, you cannot right now. There's a separate proposal for thread affinity. Okay, so OpenMP has, in fact, I designed the OpenMP thread affinity way back when I was a lot younger. I was only 50 years old at the time. So I can tell you that we are also working on a separate proposal to enable thread affinity. Okay, we need something like that. Scheduler doesn't follow thread affinity at this point.
Okay, thanks.
Okay. I'm telling you, I'm a lot older than I look. Next, please.
Yeah, I actually had the same question as the
Right.
gentleman two times or two positions before me. But it seems like the execution policy or the scheduler, they all are in the same address space. And,
Yes.
and
Yes.
yeah, if you want to move to a cluster, you would obviously have to exit the address space. But just to continue, the scheduler and the execution policy, why have they been separated? Was there an idea that the scheduler could be a variant of an execution policy? What
We
motivated
thought
you?
about that. That would create the interface in such a combinatoric explosion.
Okay.
Different parallel, different scheduler. We just thought that it was easier to just separate the two concerns.
Yeah, that's fair.
So there was a long debate about that during the executor study group that was talking about all of this.
Okay, and then the existing functions like standard reduce and standard transform, are those going to be affected by, in your mind, are those going to be affected by the developments that you're doing? Are they going to be deprecated or are they going to be
I don't think
replaced?
they will ever be deprecated. I think they will be refitted to enable this capability, right? They're never, reduce and transform are vital higher level abstractions in the standard library. There's no way we're ever going to get rid of that. All right?
Thank you.
Thank you. Next, please.
I'm not sure if this is the right group to bring this up, but I have a problem that I've been working on where I've been trying to wrap the system call interface in pure C++ inline. And I've been wanting
You've been
to
trying to do what?
wrap the Linux system call interface in pure inline C++.
Wrap a Linux system call interface, right?
Yes. And one of the things that it would be very nice to do is to say any memory accessed through this pointer argument in this range should be considered invalid. Like, But I don't see an easy way to do that currently in C++.
I wish Paul were here. This is kind of like his specialty. So the question is, exclude certain memory locations, addresses?
Well, basically, right now, compilers make all kinds of assumptions about things that they've loaded and whether they're still valid or not.
Yeah.
It would be really nice to be able to say, you know, I made this system call, it's a read, I read it to this address, the maximum number of bytes is this, so this memory range, anything that was loaded through this pointer from this memory range should be considered, it needs to be reloaded again.
Okay, I think that's more like a Paul McKenney question, So let's talk after that.
Okay.
We'll give you his email. He's probably much more expert in the Linux system kernel about wrapping wrapping a C++ interface on a C system call.
Right.
That allow you to do this.
Right, I know how to do that.
Yeah.
It's just the matter of the memory invalidation.
The memory invalidation. Yeah.
Right, which I'll ask him about that too.
Thank you. Last question before we exit.
I have just a small comment with a talk from Walter Brown of yesterday in mind.
From whose talk?
Of Walter Brown from yesterday. He gave a talk.
I'm sorry?
Walter Brown.
Oh,
Walter Brown,
yes,
yeah, he
thank you.
gave a talk about irksam C++. And on your tag pointer, you have untag pointer and tag value. I would propose to harmonize these functions, the naming of the function, untag pointer and tag
So
value.
I think he's trying to say you want to harmonize these different APIs.
Yeah, I would propose maybe rename it to untag value. Otherwise, you might end up on Walter's slides.
Yeah. So you instead of 4 or 5 different API functions, you want to bring them together and use some sort of either discriminated interface or policy or.
No, what I'm just saying is the naming. The naming is a little bit irksome.
Yeah. Okay.
You know, untag pointer you decompose it, and tag value you also decompose it, and tag pointer does
So
a
what he's
composing.
saying, if I can interpret, is like accumulate. There's a way to build up like commonalities, and before you split out to the individual functions. Okay, and accumulate is great for that kind of thing. Okay, after accumulate, you can actually, compute kurtosis or mean or median, but only up to a certain point. So I think this is a comment more for the author. This is the interface we got, and there's not much we can do about it. But this is why we expose it here. This is a time for you guys to tell us how to improve this interface. Okay, and we will have to send you to Hana Dusakova issues in Czech.
Okay,
Republic.
thank you.
So,
Okay.
yeah, the SG1 is more about like the concurrency. Oh, this is this is good, but then we
What,
can,
what you're talking about is
Is
the domain of library
elite.
evolution.
Yeah.
They look at the whole thing and try to clean it up and make it less irksome. Like we are just concurrency experts. To be honest, I couldn't tell you whether this is a good interface or not. But I believe you. Walter Brown says. I believe you. Walter Brown says it's not a great interface. Okay.
Thank you.
All right. Any other questions? All right. Well, thank you very much. Thank you. We'll try to do this every year to bring you some concurrency parallelism features, and hopefully you guys will find it interesting. We'll try to make it, easily reachable. Thank you.